Hi everyone, this is Dr. Hopkins with our next video. Here we're going to discuss formulas or molecular formulas and how to use molar mass of those formulas. Alright, so let's start. We're going to talk about or define a few things, molecules and compounds. So we dealt with atoms and elements in the last video. And so molecules are basically composed of multiple atoms. And they're typically held together by chemical bonds, either covalent or ionic. We're not going to describe bonding at this point. We will get into that in much more depth later on in the course. So basically, some elements are actually molecules, and there's several elements that are diatomic molecules. That means they have two atoms. And here I have them listed: hydrogen, fluorine, chlorine, oxygen, nitrogen, bromine, and iodine. Those are all molecules, so don't confuse elements and atoms. They aren't necessarily the same thing. Some elements are actually molecules. And then when we talk about a compound is typically composed of two or more elements. So our elements that are molecules aren't necessarily compounds. Now, compounds can be molecular, so then it's just a molecular compound, or it can be ionic. We'll talk a little bit about what that means as we get through more discussion of the periodic table, but I give an example like hydrochloric acid, so HCl. And then another definition that kind of just thrown in here, we're not going to use very much, but it can show up. There are ions, so if you have something that is charged, either an atom, molecule, or a compound that's charged, they are called ions. If they're positively charged, they're cations. Negatively charged, they're anions. And here I show examples. So how do we represent molecules? We showed in the last time we look at the periodic table, there are symbols for the atoms and the elements. And so what we do is we represent molecules with molecular formulas. This is basically a series of the elements involved in the molecule or the compound. So you'll write this particular symbol and you put a subscript number on the right-hand side of the symbol to indicate the number of those atoms, so that type of atom. So if it's oxygen and then you put a 3, it means you have 3 oxygens in this compound. And here's an example, C2H4, where each molecule has 2 carbon atoms, so that's let's get the pencil. So we've got the 2 here, and then 4 hydrogen atoms. Okay, so you put the subscript to the right, 4, and that's what that means. That's written out. Now, the way I've said it is atoms and atoms, but if you recall, it would also equal, so if we had a mole of this molecule, they would have 2 moles of carbon and 4 moles of hydrogen. So remember, just like molar mass scaled up from atomic mass units to molar mass units, or atomic mass in terms of grams per mole, so do the subscripts. And then an example, so water, H2O, each water molecule basically has the 2 hydrogens, and then 1, you don't write the 1 as a subscript, it's just implied. If there's no number there, it just means there's 1 oxygen in this molecule itself. And anytime you would see, so if we had a coefficient in front of the formula, it indicates how many molecules or how many moles of it. So if we put 2 in front of this, that means we have 2 moles of C2H4. And it's something you do when you're writing reactions or equations, which we'll get to at a later date. All right, so molar mass. So in order to determine the molecular mass or even the molar mass, remember they're basically the same numbers, but scaled up in a large number of molecules. All you need to do is sum the atomic masses. So you look on the periodic table, find all of your masses, and you sum them up. So we're going to use our previous example, C2H4. We have 2 carbons, and so we looked this up. I don't have the periodic table here. We got 12.011 grams per mole for carbon, and we have 4 hydrogens, so we put the molar mass or the atomic mass of hydrogen there, we put the 4 here, And we're left with, let's see, let's do this calculation real quick. So we've got 2 times 12.011 plus 4 times 1.008 is 28.054 grams per mole. And that would be the molar mass, and this is per mole, sorry. That would be the molar mass of C2H4. And we can extend that to, say, calcium chloride. So we've got 1 calcium. So we looked that up in the periodic table, and that's 40. And we have 2 chlorines. We looked that one up, and that's 35.45 each. So these would be, we could substitute in AMU and AMU if we were just talking about 1 molecule of calcium chloride. But most of the time we're dealing with macroscopic quantities. And so this, if we add that up while I've been talking, is 110.98 grams per mole. And so those would be your molar masses. So you could take any formula and the periodic table and figure out the molar mass. What does the molar mass get you? Well, if we have, let's say we go into the lab, we have some calcium chloride. We can't measure moles of the calcium chloride. What we can measure on a balance is grams or mass. So we can use these grams to figure out how many moles. So if we wanted to know moles for a chemical reaction, we would need to do that. So let's do this calculation. How many moles of aluminum are in 2 grams of aluminum itself? So once again, we would look up, so let's set up the equation. We look up the the atomic mass of aluminum. We can do this as kind of a dimensional analysis problem, which we've done before. So we've got 2 grams, and we want our answer needs to be in moles. The molar mass, or atomic mass, is in grams per mole. So if I divide my mass by my atomic mass, I have here how I have it written, we should get, so the grams will cancel, and you will get moles. So you get 0.074 moles. So if we wanted to know if we have grams and we want to convert to moles, it's grams divided by atomic mass equals moles. Okay, so let's do another one. Let's take, let's figure out how many moles are in 5 grams of our calcium chloride. And so here I'm gonna write it. So moles is equal to 5 grams. We need to divide by our molar mass. So I'm just going to flip it over. So we got moles. What was our answer from the previous slide? It was what, 110.98, if I can remember that correctly, right? And so we've got, that's our grams divided by molar mass. And so 5 divided by 110.98 is 0.045 moles. And that would be the number of moles of calcium chloride. Now we could take this even further, and we could derive how many molecules we have of calcium chloride in 5 grams. And basically we would just multiply that value, because we would multiply that by Avogadro's number, right? So N sub A actually is the subscript for that, which would be 0.045 moles, because Avogadro's number is the number of anything in a mole. And so then this would be, 6.02 times 10 to the 23rd. And the units on Avogadro's number are 1 over moles. And so our total number of molecules, if we multiply that out, is 2.71 times 10 to the 22 molecules. So in that simple 5 grams, we have 2.7 times 10 to the 22 calcium chloride molecules. Now we can also reverse this. So if we know an experiment requires 0.05 moles of, say, silicon dioxide or sand, and we have a balance, so we can mass this sand. So how many grams do we need to get that? So the first thing we would want to do is figure out the molar mass of our SiO2. So we would look up silicon on the periodic table and then oxygen on the periodic table, and we sum these up. I'm not going to do the intermediate calculation. I'm just going to show it to you. It's 60.08 grams per mole. So that's the molar mass of silicon dioxide. Now we want to grams, so grams of SiO2. If we just do a dimensional analysis, so we've got 0.050 moles. In this case, we don't want to divide by the molar mass. We're going to multiply it by the molar mass. All right, so this is going to be, and I'm going to put it down here, so 0.05 moles times 60.08 grams per mole. All right, so if we do the math, the moles are going to cancel. We're going to be left with grams, which is what we want. So we do 0.05 times 60.08, and we should get 3.00 grams. Now I've cut it off, it gets 3.004, but you'll notice we actually really only have two significant digits here. So this really should be 3.0 grams of SiO2, excuse me, of our sand. And that would be how much we would need to get the number of moles we require for our experiment. So here are the kind of take home from this video where we've learned about molecules and compounds. We can write formulas, we can determine molar masses, and now we can convert using molar masses between grams and moles for atoms, compounds, anything we have a formula for. And I didn't show it, and I'm not going to talk about it in any other video, at least until we get to the point where we're measuring it. But empirical formula is discussed is basically the ratio of atoms, so it's a minimum ratio of atoms. So our C2H4, the empirical formula would be CH2. It's not as common, except for in some particular measurements that we don't show and we may deal with later on in the course. So until next time.